you've got a tree. Each node on the tree has a value, either a 0 or a 1. So a tree with binary values. And you have a target configuration of 0s and 1s that you want to get this tree to. So here, for example, this node has a 0 and it needs a 0, so it's correct currently. But this node 2 has a 0 written on it, but it needs to have a 1 written on it. So it has the wrong value. And similarly, these values are also wrong. So the node number 4 has a 1 on it, but it needs a 0. And you need to fix this, and the operation you have is to just swap the values on neighboring nodes. So you could take this 3 and this 4, for example, and the 3 has a 0 written on it, and the 4 has a 1, and you could swap those two. And that would actually fix both of these in this case, because the 3 would now have a 1, the 4 would have a 0, and they would both be correct. And the question is, what's the minimum number of operations you need to fix this tree? So you're given the tree, the starting configuration, and the target configuration, and you're asked how many operations you need to perform to get the tree into the correct target configuration, the minimum number. So that's the problem. This is the easy version of the problem. The harder version of the problem also asks you to output the swaps themselves that you need to perform. But the easy version just asks for the smallest number of swaps. So how do we do this? In this problem, you basically just have to guess the answer straight away. So what is the answer? What is the answer? The answer is, let's consider each edge. For each edge, let's say this edge right here. Let's count the number of 1s on each side of this edge. Currently, we have 2 1s on this side of this edge, and we have none on the other side. So this edge has this 0-2 split of 1s. In the target configuration, we need 0 1s on this side because, both the values that we need on this side need to be 0s. And we need 2 1s on that side because there's a 1 here and a 1 here. So actually, we currently have no 1s on the top side and 2 1s on the bottom side. And we need to have no 1s on the bottom side and 2 on the top side. That means, we need to move 2 1s this way in the whole process of all these swaps. We need to move 2 1s upwards across this edge from the 4 to the 3. So what are we doing? We're considering the 2 components that would be formed if we removed this edge and just counting the number of 1s we have initially in each component and the number of 1s we need to have in the target configuration in each component and just comparing those. And so the difference between each of these values we'll call the imbalance of this edge. So 2 minus 0, or the 2 up here minus this 0, that's the imbalance of this edge. So if you take this edge and then consider any one side of it and count the 1s that we currently have on that side and the ones that we need to have on that side, that's the imbalance of this edge.